NRC Event Notification Report for March 20, 2013. Vogtle Nuclear Plant in Georgia. Emergency declared. Fire within protected area. On March 20, 2013, the licensee, Southern Nuclear, declared an emergency due to an indication of a fire in the protected area for greater than 15 minutes. Southern Nuclear received initial indication of a fire alarm and startup of fire water pumps. The alarm was located in the vicinity of the Auxiliary Building Unit 2 HVAC supply unit. Upon investigation, it was determined that the heater strips in an HVAC unit were overheated and caused a fire alarm, and no fire actually existed. Oh, goody. It's okay then. Plant Vogtle is a 2-unit nuclear power plant located in Georgia. Each unit has a Westinghouse pressurized water reactor with a General Electric turbine and electric generator. Units 1 and 2 were completed in 1987 and 1989 respectively. During Vogtle's construction, capital investment jumped from an estimated $660 million to $8,870 million. In 2009, the NRC renewed the licenses for both units for an additional 20 years to expire in the 2040s. Southern Nuclear is building 2 more untested and highly unreliable AP1000 reactors at the Vogtle plant. This truly insane project was extensively criticized by the independent nuclear experts and anti-nuclear activists. Please see links in the description area below the video. On top of all this, here is an article how one of the reactor pressure vessels made in South Korea fell off the train. The Nuclear Regulatory Commission defines two emergency planning zones around nuclear power plants. First is a plume exposure pathway zone with a radius of 10 miles, concerned primarily with exposure and inhalation of airborne radioactive contamination. Second is an ingestion pathway zone of about 50 miles, concerned primarily with ingestion of food and liquid contaminated by radioactivity. The 2010 United States population within 10 miles of Vogtle nuclear was 5,845. The 2010 United States population within 50 miles was 726,640. Cities within 50 miles include Augusta, 26 miles to city center. Finally, here's what Arnie Gunderson of Fairwinds Associates has to say about these two new monstrosities.
Hi, I'm Arnie Gunderson from Fairwinds. In the past, we've talked about how the accident at Fukushima should teach lessons to the 100 operating nuclear reactors here in the United States and the 400 operating nuclear reactors around the world. The Nuclear Regulatory Commission had a task force that evaluated Fukushima and found 40 pages worth of concerns. Well, today I wanted to talk to you about how those Fukushima lessons should be applied not to the operating reactors, but to new reactors that are being constructed in China and are being proposed right here in the United States. There are lessons to be learned here for these new reactors. But right now, the Nuclear Regulatory Commission is not insisting that those new designs incorporate any lessons from Fukushima. Fairwinds was retained by the AP1000 Oversight Group to take a look at one reactor built by Westinghouse Toshiba. It's called the AP1000 design. They asked us to take a look at Fukushima in relationship to this AP1000 design, to see if it really is safe enough. This AP1000 design is different than any reactor that's ever been built. There are several of these being constructed in China right now, and about a dozen that are proposed in the southeastern part of the United States. What makes the reactor unique is that it has a huge water tank on the roof. It's about 6 million pounds of water that sits directly above the nuclear containment. In the event of an accident, a waterfall is supposed to begin that will flow over top of the nuclear containment and take the heat away as a cloud of steam. Now that 6 million pounds will last between 2 and 3 days, and then it's empty and it has to be replenished. This design has never been tested as a full-scale test. What's the rush? There's no power requirements that are pressing in either Georgia or South Carolina. And in fact, when these plants are built, the electric rates are going to go up. They're going to go up a lot. So what's the rush? It seems to be congressional pressure is being put on the Nuclear Regulatory Commission to get these plants licensed. Industry pressure is being put on the Nuclear Regulatory Commission for the same goal. And on top of that, the states of Georgia and South Carolina are anxious to have about 4,000 unemployed construction workers have employment for the next 3 or 4 years as these plants are being built. This isn't about safety. This is about pressure being applied on the Nuclear Regulatory Commission by Congress and the nuclear industry. As a matter of fact, the NRC has actually said, well, we'll worry about the Fukushima modifications while these plants are being built. I don't think that's a good idea. I think the right way and the least expensive way would be to incorporate the Fukushima modifications in the design before the design certification is issued. I've looked at the design and I found about 6 areas where the Fukushima lessons can directly be applied to this AP1000 design. First, this AP1000 design, built by Westinghouse Toshiba, has a containment whose maximum design pressure is 59 pounds. When you do the calculations after an accident, not including any lessons learned from Fukushima, it turns out that the accident pressure is 58.3 pounds. So there's only 0.7 of a pound of pressure difference between what engineers expect will happen and what the containment is designed to withstand. Now, 59 pounds is about the pressure in a bicycle tire. And we're talking about 0.7 of a pound difference between its maximum design pressure and what Westinghouse Toshiba thinks an accident will really create. I think it's too close to the margin. And we still haven't factored in any of the lessons that we've learned here on Fukushima. The second Fukushima lesson that has not been incorporated in this Westinghouse Toshiba design is the fact that the reactor at Fukushima is continuing to generate heat from something called an inadvertent criticality well after it should have shut down. Now, Westinghouse Toshiba assumes that after an accident, the control rods fall in and the heat from the nuclear chain reaction stops. What Fukushima has showed us is that that may not be the case. There may be a chain reaction that continues even after the control rods were supposed to fall in. That creates extra heat and extra pressure inside the containment. Now, this containment is within 0.7 of a pound of pressure from what its design value is. And that means that any extra heat generated from an inadvertent criticality is going to push the containment pressure above what it's designed to handle. The third Fukushima lesson that needs to be incorporated in this Westinghouse Toshiba design is something called the loss of the ultimate heat sink. At Fukushima, the cooling pumps were right along the ocean, and the tsunami came in and destroyed the pumps. This picture shows rubble all the way along the coastline of the Fukushima reactor. That's where the pumps that cool the plant are. Well, without pumps to cool the plant, there is no way to get rid of the heat from that nuclear reactor. It doesn't matter that the diesel generators were flooded. Even if the diesels had worked, the pumps that cool the diesels and the pumps that cool the reactor had been destroyed by the tsunami anyway. This is called the loss of the ultimate heat sink, and is something that the NRC is not paying attention to in operating nuclear reactors, let alone this AP1000 design. Well, how does the loss of the ultimate heat sink pertain to this Westinghouse Toshiba design? The Westinghouse Toshiba design on the roof has the ultimate heat sink. It's that 6 million pounds of water that's designed to fall like a waterfall over the outside of the containment structure. If it doesn't work, you're back at Fukushima all over again. So the question then becomes, what could cause the tank on the roof to fail? There's a report on our website that details many reasons why that tank may fail, but basically it boils down to 3 different areas. The first is that from a seismic standpoint, the wrong place to put all the weight in a power plant is on the roof, because when the earth shakes, the top shakes more. So from a seismic design standpoint, it's the wrong idea. The second, and probably even more critical issue, is that from a terrorism standpoint, the biggest target on site is in the most easily accessible location, right on top of the containment. It's not designed for an airplane strike. And it's plainly visible for tourists if they decided that they wanted to take out the ultimate heat sink. And the third reason is, you'll recall that at Fukushima there was an explosion at one reactor that threw shrapnel into the surrounding reactors. Well, the Vogtle site and the VC Summer site have other reactors on them. If the other reactor has an accident and explodes, the shrapnel from those reactors can wipe out the tank on top of this AP1000 design. So for those reasons and others, it is entirely possible that you can have a loss of the ultimate heat sink on this Westinghouse Toshiba design. But the Nuclear Regulatory Commission assumes that the probability of this happening is zero. They assume it cannot happen. I don't think that's right, especially in light of what we learned at Fukushima. The fourth problem that Fairewinds identified for the AP1000 oversight group is the fact that the nuclear fuel pool on the AP1000 design is almost identical to the fuel pools of all of the operating reactors in the world, including the ones at Fukushima. Now, you'll remember that the Unit 4 fuel pool at Fukushima blew up. It generated enough hydrogen that it blew the sides off the building because it wasn't cooled. That same exact cooling system is in place on the AP1000 design. Yet, amazingly, the Nuclear Regulatory Commission is allowing this plant to be built, while at the same time telling the nuclear industry that it has to fix the cooling of the fuel pool on its operating reactors. Again, on the Fairewinds site and on the NC Warren site, there's a more detailed explanation about this fuel pool cooling system. The Westinghouse Toshiba design has a fifth problem. On multi-unit sites, if one unit were to explode like Fukushima 1 or like Fukushima 3, the rubble would fall onto the Westinghouse AP1000. Well, we already talked about how the rubble could damage the tank on the roof, but it doesn't stop there. This design is meant to be cooled by the water falling from that 6 million pound tank. Well, that creates a chimney, and the air is pulled in from the outside, and as the water is falling down, air is moving up along the outside of the containment, and steam comes out the roof of this containment. That's the way it's supposed to work. Well, on a multi-unit site, if one unit has an accident and throws up a cloud like Fukushima 3 did, it's likely that the dirt and the dust and the rubble in that cloud will plug the air intakes on the AP1000 and prevent its ability to cool itself. That hasn't been analyzed by the NRC or by Westinghouse Toshiba. As a matter of fact, they assume there's a 0% probability of that happening. The sixth issue that Fairewinds discovered was that this AP1000 design is really, really close to its design margin, and yet the Nuclear Regulatory Commission assumes that nothing leaks out of that containment and into the gap that then gets sucked out the roof. They assume there's a 0 probability of that occurring. Fukushima shows that we've had 3 containments that have leaked directly into the environment. Yet the Nuclear Regulatory Commission assumes there's 0 probability of that very same thing occurring. Now we'll also remember that the Fukushima Unit 3 had something called a detonation shockwave. The AP1000 design can't handle a detonation shockwave. It's way too close to its design margin right now to withstand the extra stresses that we know already happened on Fukushima Unit 3. Fairewinds came up with a report about 18 months ago on this issue called the chimney effect and the problem of leakage right into that annular gap and up out the roof. Yet the NRC has refused to look at that report and in fact has said that there's no chance that radiation can be released directly from the containment. I think it's wrong. I think Fukushima shows clearly that containments do leak directly into the environment, and the AP1000 is no exception. Finally, the Nuclear Regulatory Commission uses something called risk-informed decision-making. Prior to Fukushima, if you had asked the NRC what the chances of a nuclear meltdown were, they would have said about the same as being hit by a meteor. If you asked them what the chances of 3 meltdowns in 3 days would have been, they would have said it was impossible. And that's because they use risk-informed decision-making. Not only do they use it on their operating reactors, but they've used it on the AP1000 design as well. I think Fukushima shows that this risk-informed decision-making is wrong. They're using improper probabilities that are way, way, way too low, so that they come up with numbers that rationalize decisions that really put the risk on you and I and minimize the cost to the people that are building these reactors. I think it's time to reverse that process with the AP1000 design and to put in reasonable probabilities into these calculations so that public health and safety are really protected. Last year, I met with the Nuclear Regulatory Commission about the AP1000 design, and I had concerns. I got the impression in that meeting that there was nothing anyone was ever going to do to stop this design certification from being approved. Since I met with the NRC, there's been 3 nuclear meltdowns. Now you'd think that the Fukushima accidents would cause the NRC to stand back and say, what have we been doing wrong? What should we do to make these plants safer? That's not happening. What's the rush at the NRC? They are pushing rapidly to give a design certification to the Vogtle units and the VC summer units. And to my mind, there's no pressing need. America doesn't need the power. Georgia and South Carolina have more than enough. And when the plants are going to be built, the cost of power from them is going to be higher than anything they could buy from any other source. It doesn't make sense, except for the political pressure that's being applied. Well, this full report is on the Fairwinds website and on the NC Warren website. I urge you to read the full report, and if you have any questions, please contact NC Warren at the phone number that's displayed on your screen. Thank you very much. For Fairwinds, we'll keep you informed.
NRC Event Notification Report for March 20, 2013. Vogtle Nuclear Plant in Georgia. Emergency declared. Fire within protected area. On March 20, 2013, the licensee, Southern Nuclear, declared an emergency due to an indication of a fire in the protected area for greater than 15 minutes. Southern Nuclear received initial indication of a fire alarm and start up of fire water pumps. The alarm was located in the vicinity of the Auxiliary Building Unit 2 HVAC supply unit. Upon investigation, it was determined that the heater strips in an HVAC unit were overheated and caused a fire alarm, and no fire actually existed. Oh, goody. It's okay then. Plant Vogtle is a 2-unit nuclear power plant located in Georgia. Each unit has a Westinghouse pressurized water reactor with a General Electric turbine and electric generator. Units 1 and 2 were completed in 1987 and 1989 respectively. During Vogtle's construction, capital investment jumped from an estimated $660 million to $8,870 million. In 2009, the NRC renewed the licenses for both units for an additional 20 years to expire in the 2040s. Southern Nuclear is building 2 more untested and highly unreliable AP1000 reactors at the Vogtle plant. This truly insane project was extensively criticized by the independent nuclear experts and anti-nuclear activists. Please see links in the description area below the video. On top of all this, here is an article how one of the reactor pressure vessels made in South Korea fell off the train.